See second application, that is finding connected components in undirected graph. How to find out connected components? We know that when you have a graph like this, A to B, B to C, let's say, and D to E, E to F, this kind of graph. We say that there are two connected components, correct? Did you remember one thing? So first of all, if you understand DFS algorithm, how it works, first we call DFS on A, let's say. Then DFS of A calls DFS of B, and DS of B will call DFS of C, correct? And after that what happens, you don't get any new neighbor, you go back and we start DFS of D, correct? So if you understand DFS algorithm, you realize that DFS of D will be called from the main program. There are two programs, one is DFS initiator, I can say, second one DFS method, right? So first we come to DFS method, after that we'll go back to DFS initiator, and again we get a call from DFS on D. Then that DFS of D will call DFS of E. So DFS of E will call DFS of F. So this is the way this DFS algorithm works, correct? Now what I want to say is, this is DFS of A, you got this call from main program, right? That is DFS program. Did you remember in my implementation there are two things, one is DFS, second one DFS visit, right? So DFS visit is a recursive program. So we had a for loop here in DFS. So for every vertex, so there was a code like DFS, correct? Like DFS visit call. So this is a rough outline of our program. So what I want to say is, whenever you come back to, once this DFS visit is done, then we'll come back to this DFS, this main program, and because of for loop, again one more DFS will be called, correct? So first time what happens, DFS of A will be called, because of this DFS visit, on A will call B, on B will call C, after that, so nothing new will be found, then this DFS will be closed. When this is closed, then we'll come back, and because of this loop, we continue again doing DFS on D. So my suggestion, please go through that code before attending this lecture. So then you realize that first again DFS of D will be called, on that E, on that F. So what is one important thing I would like to say is, here this entire calling sequence happened because of this DFS visit. Here you maintain counter, okay? So let's say initially counter is 0. So whenever in this for loop, if you maintain counter plus plus, whenever this DFS visit call is successful, then what happens, this first DFS visit made this DFS of A call, after that subsequent calls are made because of this DFS visit, right? So I am assuming that you know that code, okay? So here this DFS of D again is called from this DFS visit, that's why. So this counter plus plus, if you maintain, this counter is going to count number of times you called this connected, this DFS, correct? So now if you see, for entire connected component, this one, we will make one DFS from here. After that we'll come back, and again on this behalf of this connected component, we make one more DFS of D. But further subsequent calls E, F are made through here, correct? So I can say that the number of M for every connected component, there will be a call here. Then if you maintain a counter here, and if you count the number of calls, then we can get it, correct? So finally finding the number of connected components problem is nothing but after all DFS, but only one line to be added. That's why the time complexity is order of V plus E. So simple, right? Now we'll see how to find out number of connected components in undirected graph. Okay, that is also one more easy problem. Example, let's say you have graph like this, A to B, B to C, A to C, and let's say D to E, E to F, D to F something, and G to H something like this. So what I do is I call DFS method. There are two components in DFS method. One is DFS, second one DFS visit, right? So I'm using that program. So please go through that program and execute for some graphs you understand and make comfortable with that program. Then come here. So in DFS, so there is a DFS visit call, right? So this is the first call. Because of that, we will go to this program. This is second method. This is main method, okay? So here this DFS visit is embedded in for loop, right? There is a for loop. What I want to say is, first of all, if you really understand DFS code, so first DFS of, because of this code, DFS visit will be made on A, correct? Assume that, let's say A is the first vertex in the list. So A is the first vertex, then we'll call DFS visit of A. So after that what happens? A will call DFS visit of, correct, B. Then after that, that will call DFS visit of C. Then you realize slowly there is no new vertex. Then go back. Then this DFS entire method will be closed. Once this is closed, we'll go back and again we'll have DFS visit on another vertex, which is either D or E or F, depends on the order of vertices your program is taking. So on every component, on behalf of every component, so this DFS visit will be executed, correct? So that's why I can say that if you maintain here counter, what happens if I initially keep counter 0 and if I increment every time when DFS visit made, then so DFS visit first time will be made here. After that, for subsequent B comma C, it will not be made, right? This DFS B and DFS V of B, DFS visit of C are made because of this. There is another DFS visit here, right? So you know that DFS visit. So this DFS visit because of this one, right? Because of this main program's DFS visit, so one call will happen here, another call will happen here, another call will happen here. For every different component, one call will happen. That's why if I maintain here counter, that will count the number of connected components. That's why finding connected components in the undirected graph is very easy, like finding cycles in the graph. So that is order of V plus E, correct? Because after all you are doing DFS.